Hi, my name is Joe Vincent. I'll be discussing the paper I authored with Max Schwager titled Reachable Polyhedral Marching, a safety verification algorithm for robotic systems with deep neural network components. Suppose we train a neural network to approximate the discrete time dynamics of a damped pendulum. We can compute the state multiple time steps into the future by composing the neural network with itself. Suppose we sample the following 50 time step trajectory and would like to determine if damping behavior was in fact learned for all trajectories over some set of initial conditions. We compose this as a forward reachability problem and use our RPM algorithm to solve for the forward reachable set. The figure on the left shows the set of inputs plus or minus 90 degrees plus or minus 90 degrees per second, as well as the superimposed forward reachable set, which is also blown up into the figure on the right. So we can see that all states in our starting set tend to converge towards the origin over time. Additionally, note that our exact forward reachable procedure allows us to identify the true non-convex forward reachable set. You'll also notice that the input set as well as the reachable set are actually the union of a bunch of smaller polyhedral sets. This is because our dynamics function is a neural network with ReLU activation, and this is actually a piecewise affine function. So our dynamics function is affine over each of these regions, which is critical to our reachability analysis. The next example I want to highlight is an analysis of neural network controllers. So here we look at the ACAS-XU policy networks. These are aircraft collision avoidance networks that have 5 inputs, 5 outputs, and 300 neurons. Inputs are relative pose and velocities of 2 aircraft, and outputs are recommended actions to avoid mid-air collision. One of the safety properties which should be adhered to is if the intruder is directly ahead and moving towards the ownership, the network will recommend turning left or right. We look at 4 of the policy networks and find that 2 out of 4 are unsafe. And those which are unsafe, we see that we're able to certify the unsafety of these networks much faster than current methods. This is due to our early termination property. For networks which are safe, we are roughly 2 times slower than the state-of-the-art, but still enjoy considerable speed up compared to other exact methods, such as ReLUplex and Marabou. We propose novel forward and backward reachability algorithms that incrementally compute exact reachable sets of ReLU neural networks. Our algorithms allow for early termination, which certifies neural networks as unsafe many times faster than current state-of-the-art exact reachability methods.